Hey PCH, so this ed puzzle is going to prepare you for our last lesson of this unit, which also just happens to be the last lesson of this trimester before finals, so let's really make it count. And this lesson is going to be over trig identities. Now, we'll get into exactly what trig identities are, but if you're looking at the problem on our screen right now, we see that somehow we're supposed to prove that whatever's going on the left side of this equation is equal to 0. And with what we know right now, we don't really know if there's anything we can do at all because we don't know how to rewrite any of these things like 1 minus cosine into something else that might help us get the left side of this equation equal to 0. And that's what trig identities are going to help us do. And so a few of the trig identities have to do with even and odd functions. And so to begin this ed puzzle, I want us to do some even odd fluency. And all I want you to do simply is look at each graph and tell me, is it even or odd? We talked about even and odd functions way back at the beginning of Try 1, and some of the things we talked about are listed on my screen here that you can see. When we have even functions, we know that those functions are symmetrical over the y-axis. When we're looking at this graph for number 1, we see that if we were to, if this graph was a piece of paper, and we folded it in half with the y-axis being our crease, whatever's on the right half of our paper is going to directly match up with whatever's on the left half of our paper. Another way to think about that is that if we have the point x comma y, and we can think about it like maybe the point positive 2 comma positive 4, we should have the point negative x comma positive y. Negative 2 comma positive 4. And we do have that point here. And so number 1 is going to be an even function for us. What we notice about odd functions is that they're symmetrical about the origin. If you were to take your graph and turn it or twist it 180 degrees, and it looks the same, then you're going to have an odd function. Another way to think about that is that if you have the point x comma y, we'll say in number 2, the point positive 4, negative 1, we should have the point negative x comma negative y. So negative 4 comma positive 1. And it looks like we do. And so graph number 2 is going to be an odd function. In the same way, number 3 is odd, and number 4 is even. And it's pretty easy to see that when we're talking about symmetry over the graph. Another way to think about this, and it's kind of like what we were just talking about with our points here. I'll draw arrows here. We know a function is an even function when if we plug in negative x into the function, we're going to get f of x. We're going to get the same y value that we would have gotten if we plugged in a positive x. And we talked about that, right? Positive x comma positive y. We are also going to have the point negative x comma positive y. The same y value regardless on if our x was positive or negative. An odd function is different because, again, just like we talked about, if we plug in f of negative x, that's going to give us negative f of x. If we plug in negative x, we're going to get our y value having the opposite sign from when we plug in just a positive x. And so keeping those things in mind, and I encourage you to pause the screen for a second and really try and make sure you understand what this notation means, we're going to talk about our first trig identities. Now, our trig identities, of course, are going to have to do with sine, cosine, tangent, our trig functions. And so we just did some fluency on some random functions, but let's talk about sine, cosine, and tangent. And you tell me, is sine an even or an odd function? Is cosine an even or an odd function? And is tangent an even or an odd function? Feel free to draw some pictures of the graphs of those if that would help you. When you graph sine, cosine, and tangent, you can really easily see that both sine and tangent are odd functions because they're symmetrical about the origin, and cosine is an even function because it's symmetrical over the y-axis. Why does this mean something to us? Well, we can think about what this means in terms of symmetrical identities. If we're ever facing a problem where we see we have sine of negative x, based on what we talked about, the fact that sine is an odd function, and we said that if function is odd, when f of negative x, so in this case sine of negative x, is going to equal negative f of x, negative sine of x. And that's going to be one of our identities. So sine of negative x, is negative sine of x. And that gives us a way to get that negative outside of our argument. Cosine's an even function, and so cosine of negative x, that is simply going to equal cosine of x. Tangent's odd, so it'll be negative tangent of x. And of course, because cosecant, secant, and cotangent are reciprocal functions of sine, cosine, and tangent respectively, we know that if sine of negative x equals negative sine of x, cosecant of negative x is going to equal negative cosecant of x. Sine is an odd function, cosecant is going to be an odd function as well. Now, before we move on to some other identities, let's think about this question. Why do you think these are called the symmetry identities? Hopefully you said something about the fact that based on the fact that these functions are even or odd, and based on what type of symmetry they have, that tells us how we can rewrite them, how we can get that negative outside of our argument. And so that's why these are called the symmetry identities. Let's move on to our next set of identities, which are the reciprocal identities. And you know what, folks? We already know what these reciprocal identities are. Right, we've been talking about the fact that sine and cosecant are reciprocal functions since the beginning of last unit. Sine of x can be rewritten as 1 over cosecant of x. Cosecant of x can be rewritten as 1 over sine of x, and so on and so forth, as you can see in this table. Now, one thing you should know that whenever we're talking about using trig identities, we are always wanting to get things in terms of sine, cosine, and tangent. And so we are never going to be using these reciprocal identities on the left. We're never going to rewrite cosine as 1 over secant. What we're going to want to do is, if we see cosecant, secant, or cotangent, rewrite those trig functions in terms of their reciprocals, if that's what needs to be done. All right, how about our next set of ratio identities, which again, you all know. We talked about the fact that tangent of x is sine of x over cosine of x. And because cotangent is the reciprocal function of tangent, cotangent of x is cosine of x over sine of x. And so PCH, we have talked about 1, 2, 8, plus 6 more is 14 different identities. You already know 8 of them. And these identities up top, based on what we know about even or odd functions, these aren't really too difficult to understand either. And so while it seems like we're learning a lot of new things, a lot of these identities that we haven't really thought about or seen before as identities, it isn't entirely new information to us. So don't let this, the sheer number, overwhelm you in any way. So based on what we know, let's work on some basic level 1 proofs. So back in geometry, you talked about proofs, right? You had to set up this table, one side being like all of these different theorems you knew, these things you knew about triangles to help you prove something to be true. These are not the same kind of proofs as that. These are so much more fun, and you'll see that coming up here. But when we're talking about these types of proofs, where we're going to have to use trig identities, essentially what we're trying to do is get one side, we're trying to change one side of this equation to get it to equal the other side. And typically, whenever you're talking about trying to solve some proof, you're trying to mess with the side that looks a little bit more complicated, which is the left side, right? We have 2 different trig functions being multiplied together to be equal to whatever's on the right side. The first step is going to be to underline the side that you are working with, the side that you're going to use our identities to change and manipulate to get it equal to cosecant of t. Now, when we were talking about our trig identities, I'm going to start with cotangent just for sake of conversation, right? If we go back to our identities, well, okay, we have one trig identity for cotangent. We could rewrite it as cosine over sine, but we also have this trig identity where cotangent can be rewritten as 1 over tangent. And so we have a choice to make. We have to think about what makes the most sense. Well, if I'm trying to think about this, cosecant, which is what I see on the right side, which is what I'm trying to get, can be rewritten as 1 over sine, right? That's a reciprocal identity we just talked about. If I rewrote cotangent as 1 over tangent, that's not going to help me get to 1 over sine of t or cosecant of t in any sort of way. But if I rewrite cotangent of t as cosine of t over sine of t, then I see that sine pop up. And so that's what I'm going to lean towards. And secant of t, we only had the one trig function to rewrite that as, because there's no negative x, there's no negative argument. And so we can rewrite secant of x as 1 over cosine of x. So let's go ahead and do that. Secant 1 over cosine of t. It is super, super important that you have that t. If you just write 1 over cosine, that is not correct. Our trig functions have to have their arguments with them. Secant is 1 over cosine of t. Cotangent, we decided to rewrite that as cosine of t over sine of t. That's one of our ratio identities. I notice now, okay, my cosine of t is going to cancel out with my cosine of t, and so I am left with 1 over sine of t. 1 over sine of t is cosecant of t is equal to, cosecant of t. We've proven that secant of t times cotangent of t is equal to cosecant of t. Could I have just stopped once I saw that this cosine of t canceled out in the denominator and numerator of these two fractions being multiplied together? Could I have stopped there? What do you think? No, and that's the important part of proofs too. You can't just stop once you see the connection. Oh, I see when I cancel out those cosines, I'm going to get 1 over sine, which I know is cosecant, so I'm good to go. That's far enough. No, you are not done with the proof until you have in your final step cosecant of t is equal to cosecant of t. Now, of course, just having that means nothing to me, right? I can't just see, I need this side to be cosecant of t, so I'm just going to set it equal to. And that's the cool thing about proofs for us, is that it's not necessarily our final answer that's most important for us. It's the process. It's the work that gets us to this final step of cosecant of t being equal to cosecant of t. One last thing that we need to do in order to say, hey, I am done with this, I have proven that these two things are equal to each other, is a sign off. That can either look like a big check mark, you can draw a star, you need to have some sort of sign off telling me that yes, I have proven these things to be equal to each other, the sides of this equation to be equal to each other. Feel free to be creative. One thing that we will talk about in class tomorrow is writing QED, which I believe in Latin means it has been satisfied. We have proven this. It's been satisfied. And you're also fine to write that. You will see that in a lot of upper level math textbooks for proofs that have been finished as their sign off. All right, I want you to try number 2 and see what you can get. This one wasn't too difficult, right? My first step was to highlight or underline, somehow mark the side of this equation that I'm going to manipulate. I chose the left because it was more complicated. One thing I mentioned was that when we're talking about proofs, we're trying to get everything in terms of sine and cosine. And so this sine of t, I'm just going to leave there because it's already in terms of sine, right? I rewrote cotangent of cosine over sine of t. I see those signs cancel out, so I'm left with cosine of t is equal to cosine of t. Boom. I'm going to sign off, and we are done.